Good morning. There's a handout here. So it doesn't have handouts. Okay, so let's continue on the obtaining this discrete state space model. Okay, basically we're trying to obtain the discrete state model from a pulse transfer function. And in the previous lecture, we mentioned that there are basically two different ways. One way is you can obtain that from this difference equation. Okay, so the difference equation is basically the equivalent part of a differential equation. So under this approach, what you do is essentially you have to choose your state variables properly. Okay. And then you'll be able to create a state space model. And the other approach is today that we're going to show you here is basically what you need to do is from the pulse transfer function, so from the PTF, we can draw the so-called simulation diagram. Okay. So we draw properly the simulation diagram, and there actually are different ways of drawing the simulation diagram from the pulse transfer function. And then from the simulation diagram, based on the diagram, we can choose, okay, the state variables, okay, and then we build, okay, the state space model, okay. So this is what we're going to look at it today. So without losing any generalities here. So let's just define our pulse transfer function as a fairly general formula here. It's a numerator over denominator, and the numerator is so this is the numerator and denominator. Okay, yeah. And I'm writing it in the descending order in terms of the z to the power negative. Okay, so it's a sort of a DSP format. Different textbook, probably even our own textbook, they probably use a slightly different basically notations in terms of the coefficients that are here, right? If you want to basically make use of any of the formula, okay, yeah, then
is this handout in the complex notes?
it's a complement to the notes. Yeah, so you'll have a separate notes. So this is more of a summaries. So if we're going to derive basically certain results, and the results is based on this model here, okay? And if you're going to use the results, then you got to be able, you got to understand that you're sticking to the notations that are here, right? Yeah. If you see a different, from a different textbook, see a different results, that doesn't necessarily mean we're wrong, okay, or they are wrong. Okay. Okay. So this is pretty general here, and what I'm going to do is I'm going to actually use a more specific case to go over this kind of a structure here. Okay, so the first one, look at the first one, case number 1, is we're going to construct the so-called control canonical form. Okay. So control canonical form. We'll focus on there are different formats. Basically, it's all about, if you remember that state space model, you have x of k plus 1 here, a x of k, okay, plus u of k, right? Okay, it's all about the format of this matrix A. Whatever the matrix A format is, right? We'll see that two common ones: control canonical, observable canonical, and there are also diagonal formats. There's also maybe Jordan diagonal format. So it's all about this matrix A here, or maybe it's just arbitrary, general format. Okay. So let's look at an example. And look at this g of z equal to, okay, y of z over u of z equal to this, okay, 0.5 z squared plus z over z cubed, 0.6 z squared plus 0.5 z plus 0.3, okay? So this is a special case, right? This is a special case of this guy here. Okay, yeah. Okay, so in typically, the order of the denominator, it should be higher than the order of the numerator, typically. Okay, it's actually, I'll show you basically later. This is to satisfy the causality of the system. Okay, so the numerator at here, the order of the numerator should not be higher than the order of the denominator. If that's the case, then the system is actually not causal, right? Okay. So anyway, so here's a special case study here, and let's say in this particular case, the degree of this numerator is 2, and the degree of this denominator is 3. Now, this format is not exactly as, right, what I'm written in here. So let's divide both the numerator and denominator by z cubed. So let's see, what do we get now? And the numerator becomes what? 0.5 z negative 1, negative 2, and then 1 plus 0.6 z to the power negative 1 to the power negative 2 and to the power negative 3, right? So now this is exactly in the format, okay, as the as this general formula, okay, general model here. Okay, yeah. Okay, so let's compare the coefficients here. Let's say make sure what do we have here. So in this particular case, the coefficient for the z to the power negative 2 here is b2. So this is b2 here, right? b2 equal to 1. And this coefficient here is b1 is 0.5. And b0 equal to 0. Okay, yeah. So in the bottom here, and this is a1, and this is a2, and this is a3, right? Okay. So, okay. So now let's manipulate this thing here. We're going to try to build a simulation diagram. Okay. To build a simulation diagram, here's the next thing we're going to manipulate here. Okay. So I'm going to let this g of z. Okay. This is g of z equal to y of z over u of z. Right. Okay. So we're going to introduce an intermediate, okay, function. Let's call that h of z. So we're not changing anything at here. Just introduce an intermediate function at here, and let's rewrite that slightly here. Put h of z over here, and then h of z over u of z. Okay, so it's an intermediate z function. Okay, so here is your y of z over u of z. Now this y of z over h of z, so we're going to define this as this. So y of z over h of z, I'll define it as this numerator here. Okay. Okay, define it as a numerator. And this h of z over the u of z, I'll define it as this 1 over the denominator. So then basically this way, once you multiply these two together, there's no change, right? Okay, so that's the manipulation in here. And now, based on these two expressions at here, so from the first expression, what is y of z? Multiply the h of z to the other side. Okay, multiply h of z to the other side. So what do we get? We get 0.5 z 1 delay times h of z. Negative 2 times h of z. Okay, so 1 delay times this, 2 delay times this, right? Remember z to the power of negative 1 represents is 1 delay. And from the second one here, the h of z, okay, h of z equal to, what is h of z equal to? So h of z times the whole denominator here, right? Times the whole denominator equal u of z. Okay? And h of z times whole denominator, you have h of z times 1. h of z times 0.6 z to the power negative 1. And then times this. So we can move all of h of z and that u of z together, but then single out this 1 h of z here. So we should get u of z subtract 0.6 negative 1 h of z, 0.5 negative 2 h of z, minus 0.3. Okay, so this is from here. Is that good? Yes, this is purely algebraic manipulations, right? Any questions? Yeah? Okay, so now I'm ready to build this simulation diagram here, okay? Just based on these two expressions. Okay. So you can see both u of z and both u of z and both y of z and h of z, they start with this. So let's say we start with, okay, so this is my h of z somehow. This is the function, this is the signal h of z. Okay, this is h of z here. And what does this y of z, how does this y of z is obtained? How is y of z obtained here? It's h of z passing through 1 delay, right? Passing through 1 delay. Okay, and the signal out of this delay at here, and then times 0.5. Okay, times 0.5. Make sense, right? And then z to the power negative 2 is 2 delays. So which means what? You basically just passing through whatever it is here for another block delay. Okay? Then the signal out of here is z to the power negative 2 h of z. And the coefficient here is 1, right? Coefficient here is 1. Okay? So what we do is we can just multiply by a 1 at here. Okay? So then altogether these two somehow, okay? When you add these two together, that should give me what? Y of z. Yeah? Yeah. Okay? Yeah. Okay, so now let's look at how is h of z obtained here, right? So we built the rest of the diagram based on the second expression. Okay? Yeah. And h of z is obtained by u of z subtracting the rest of the term here. So u of z is the input. So let's say I have a u of z as an input at here, okay, as input here. Okay, so u of z, this signal is subtracting here, 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 and z to the power -1, h of z is whatever here, right? It's this. So basically, you need to feed back from here. Okay, let's say we have a negative feedback here. Okay, so it's all negative feedback. Then what are we feeding back? Feeding back this guy here, but you go to multiply by that makes sense, right? Okay, so this guy subtract 0.6 times z to the power -1 h of z. That's the first subtraction, right? Yeah. And then the other subtraction is 0.5 times z to the power -2 h of z, and that's this guy here, right? So this z to the power -2 h of z is this signal. So we need to have another one in here, 0.5, and then okay, feedback here. Okay, yeah. Well, there's one more right here, right? There's one more. So which means we are gonna delay another block right here. Okay, and the signal out of here will be multiplied by 0.3, and then feed back this guy. Okay, there we go. Right, and that finished this loop, okay, of this simulation diagram. That makes sense? Yeah. So this is actually called a standard programming. Okay, standard programming. Okay, yeah. Any questions? Yeah. Okay, so let me ask you a question now. So what if the numerator, so the question is, if the numerator, okay, equal to 0.5 z squared and z plus 2. Okay, so I added one term. So the numerator here is, there's a 2 added here compared to the original one here. Okay, so just plus the 2. Okay, if that's the case, how would you modify? So if I plus the 2 added here, how would you modify this simulation diagram? Right, so look at it. Where, how would you, what would you add basically, right? Where are you gonna add? So when, if there's a plus 2 here, so what would change? Will the bottom change? Will this equation change? Right? Yeah. And this is going to change, is going to be for this guy here, right? So the change at here is actually going to be what? Plus 2 times. Okay. Yeah. So that means from this simulation diagram here, where should we add? We should add what kind of block here? 2 times z negative 3 h over z. So where's that z and negative 3 h over z? Here, right? Here, this signal. So that signal times a block of 2, gain of 2, and feed it here. Okay, it will give you the updated ones here. Okay. Yeah. Okay, so let's still stick to the previous one there. Okay, still stick to the previous one. Here's a simulation diagram. So how will we do, okay, to obtain to obtain the state space model based on the simulation diagram. So now you do have several options starting from here, but one fundamental option that you should remember is, okay, you should always define a state variable, okay, as the signal, okay, and after this Z block, okay, the delay block here. Yeah.
So if you get a question that your numerator is a degree higher than your denominator, should you continue on, or should
you can continue on. Yeah. So basically, if the numerator is higher than the denominator, what happens is you need to use the long division first. You know, it's like a 7/5, right? So what happens? What do you get? You get 1 plus 2/5, right? So same thing. If you do get that kind of things, you need to basically extract out whatever that additional one there, and plus a standard format. Okay. Yeah.
Is it actually physical to have a larger numerator?
No, it's not. Yeah. So even if you have numerator degrees the same as the denominator degrees, right? Basically, it's still causal in that case. Okay. So when we build the diagram, as you're going to see that there is basically one particular parameter will show up. Remember, the other one is y equal to cx of k plus du of k, right? Yeah. So the additional one will show up here. But just to give me 1 second here, we'll see that. Okay. Yeah. Okay. Yeah. Okay. So how do we choose the state variables here? Choosing state variable, the rule of thumb is you choose the state variable as a signal, okay, outside this one delay here. So basically, you choose the state variable here, here, here. Is that good? And the system has an order of 3, right? System order is 3. So you need to choose basically 3 state variables here. Now the only question is, you know, should I choose this as x1 or should I choose this as x1? Right? So you have x1, x2, x3, right? So the choices of which one is x1 actually makes the space model will look different. Okay. So let me try this first. I'll choose this as a state variable x1 of k. Okay. And then I'm going to choose this as x2 of k. And then I choose this guy as x3 of k. Okay, so that's the rule of thumb. You choose your state variables, okay, right after the one delay. Okay, each z to the power -1 delay block. Okay. So as a matter of fact, if you learn a modern control system, when you build them, you probably also you can build a simulation diagram, and in that particular case, each block instead of z to the power -1, and each block in that case is actually 1/s. Okay, so you can choose a state right after that block there. All right, so this is x2 of k, but I can also write this guy as what? See, this is one delay. After one delay, you get x1 of k. So then, at this place, this is actually also x1 of k plus 1, right? Okay. And over here, it's also x2 of k plus 1. And then over here, which is x3 k plus 1. Make sense? Yeah. Okay. So now we're ready. Let's see how do we construct this model now, right? Okay. So based on the notation and here I just written. So apparently, you see, your idea is right. It's you stick to this idea here. You're trying to obtain the relationship between x of k plus 1 and x of k, right? That's what you're trying to get. Now, what I'm getting here is I'm getting x1 of k plus 1. How does that relate to the rest of state? x1 of k plus 1 actually the same as x2 of k, right? And x2 of k plus 1 is the same as x3 of k. What about x3 of k here? x3 of k, what does that equal to? Well, there's no x4, right? No x. So x3 of k equal to what? Equal to basically u of z minus whatever over here. Right? So x3 of k is the same as h of z here. Okay. So x3 of k equal to u of z subtract whatever signal over here. Okay. So I'm gonna basically plus at here. Instead of I'll write this u of k at the end of this expression in here. Okay. Yeah. So what does it subtract? It's subtracting 0.3 times which signal? 0.3 times x1, right? So negative 0.3 times x1 minus 0.5 times which one? x2, and minus 0.6 times x3, and then plus the u of k, right? Okay. So this is the three, basically the state space state equation here, basically, right? The three state equation relating relating the k plus 1 to k. Okay. So then I can write my state, okay, space equation. Basically, this is the state equation here into a matrix format. Okay, so what's the matrix format here? Okay, so for this matrix, first row is, what is it? Based on the first equation, 0, 1, 0. Second row is 0, 0, 1. And third row is okay, yeah. That's the state space model, right? Obtained based on the based on that simulation diagram and based on that choice of the state variables. Okay, yeah. And this system matrix A at here is what we call the control canonical form. Okay, and why is it called this? Well, in one of the lecture we'll talk about that. Okay, yeah. So in other words, actually, the system is it's controllable basically. Okay, for this system, controllable. Okay, as long as you can put your state space model into a control canonical format, and the system is controllable essentially. Controllable, as we're going to learn, essentially you can, for giving any initial states and given a desired final state, you can bring that from the initial one to the desired one, okay, by applying a certain set of basically control inputs. Okay, yeah. So what's the output here? Okay, output y of k. Okay, so based on this diagram here, y of k equal to 0.5 times this plus 1 times this, right? Okay. Okay, that's the output. Put in the matrix, and the first term 0, 1, and 0.5. Okay, yeah. Okay, very good. Okay, so now I'm doing this for a very specific case, right? Okay. If you remember at the beginning, I did have this here. So I said 0.5 is B1, and the 1 is B2. 0.6 this, 0.5, 0.3 is this. All right? Yeah. So if I put this, okay, this equation here back into the coefficients for that particular equation, so what we're gonna get? So this negative 0.3. So what do you say 0.3 again? 0.3 is which one? A3, right? So this is negative A3. Negative what? A2. Negative A1. Okay? Yeah. And what about the output equation there? So output equation is a little bit complicated here, but so what's this term? This is B what? B2, right? That's right. This is B1, right? So what's 1 again? 1 is B2, B2, and B1. Okay? Is that good? Yeah? Okay. So, as a matter of fact, in this particular case, based on numerator here, the B0 is 0, right? The B0 is 0. Okay? The B0 is 0. So this is basically, I'll go from here to a more general case. Okay? What if you have a very general case that is here? And that's the diagram that you see in this case. Okay? If you have a very general case and you build this simulation diagram, and this is what you see in your handouts here. Okay, basically, you just need to add one block for the Bn. Okay, for the Bn that are here to make it the same as this generic expression. All right. Yeah. Is it okay? And you can do the same thing. You can define essentially the state variable. So remember, how do I define a state variable? Define a state variable here, 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 right? Okay? Yeah. You're going to define n number of state variables, and then you can construct a state space model. And the state space model you constructed, okay, will end up with very similar ones. So here is the state equation. Okay. So the state equation, if you reduce that to order of 3, right, it gets exactly the same thing as we just obtained. And you also get the output equation at here. Okay. So look at the output equation. Output equation has this coefficient B0, 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 B0 here, right? In that example that we just finished, what's the value B0? 0. So this is why you see there's no this term, and there's no this term, no this term, no this term. There's only Bn, B minus 1, B1 here. In our case, we don't have B3, so we only have B2 and B1. Okay, that's what it's like that, right? Okay, yeah. So this B naught, right? You were asking there. So this B naught shows up at here, huh? Shows up here. Okay. So what if you have, as Dean asking, what if you have your numerator has a higher order than denominator? Then what can you imagine like this? Basically, what you can imagine is you have a numerator not S over the denominator, but the order here is higher than this. So let's say if it's higher by let's say maybe this is Z cube and this is a Z square, that kind of a case, right? Yeah. So what would you expect? You actually would get an additional term like a Z over here, right? And then plus the rest of this, okay? Not just maybe Z squared and maybe 1 like this, okay? That make sense? So you'll get an additional something like this, and then a fraction. And this fraction is the order of numerator is less than the order of denominator now, right? Okay, yeah. So that particular term right here, okay, and that particular term right here, when it show up, okay, in the end on the output, so you would have what? Can you imagine what would you have at here? Beside a u of k, you would have, what would you have? So let's look at this guy. Let's look at a particular like a case like this. So just for example, this is your current y of z over u of z, right? Okay. So let's suppose that you end up with a z plus a certain numerator over denominator. Then the y of k, so instead of y of z, I'll just write y of k here. Yeah, the y of k equal to this guy times u of k times z, right? U of k times z. U of k times z. Z itself means what? When anything times z, or u of z times z, basically what's that gonna give you? Anything times z to the power negative 1 give you 1. Anything times z to the power negative 1 give you what? A delay. So anything times z give you a future. So this is not z u of k now. This is going to be u of k plus 1 now, right? When you have a z here. Does that make sense? So, and then plus whatever the rest of them that should be. Okay? So, if you just simply look at this relationship here. So in other words, in the end, you would have something here, a u of k plus 1, right? Okay? So, what does it mean in here? What's u? U is the input. What's y? Y is the output. So, what does it mean? So, the current output, y of k, actually depends on the future input, right? So that's why what we call that. That's not a causal system. Okay? Yeah. You learned about the causal system. Causal system cannot depend on the future. Causal system, the output can only depend on the present and the past inputs. That's causal, right? Yeah. So when the numerator share the same order as the denominator, you can have basically the output depends on the current, right? Inputs. Okay? Yeah. Does that make sense? Okay, so make sure you understand that the reason behind that the order differences there, right? Okay. Okay, so I want you to exercise this. Say I choose this as x1, x2, x3, right? What if I choose reversed order? What if I choose this as x1, this is x2, and this is x3? How will the state equation look like? Okay, how will the state equation look like? So you should try this by yourself. Okay, so if this is x1, x3, and x2, and an x3 here, right? How does this space equation look like? So it's not going to be like this anymore, right? Yeah. So you can have a shortcut. You actually will see that quite easy. So in the summary that I give it to you, okay, I have the other case for the more general ones there. Okay, so but both of them. So it doesn't matter, how you define the state variables. Okay, however you define the state variables, you're always talking about the same system. Okay, the bottom line is you're talking about the same system here. And that having said that, that basically means giving a system like this, how many possible state space model can we generate? 1 or 2 or 3, right? Or infinite. Yeah? So basically, giving a system, you actually can have infinite number of ways to generate a state space model to describe the same system. And it all depends on how you define the state variables. Okay? Yeah. So if you look at the 3 state variables over here, right? They're basically the signals somewhere residing inside the simulation diagram here, right? Yeah. They don't necessarily represent a physical quantity. Okay? Yeah. So bear that in mind here. Okay? You can have an infinite number of solutions in terms of state space model. Okay, so the second one here is, okay, let's look at the observable canonical form. Okay, observable canonical form. So how do we construct this observable canonical form here? Okay. Yeah. So same way is we need to come up with a simulation diagram here, right? We need to come up with a simulation diagram. Okay, so I'm going to use the same system and to create the simulation diagram. But this time, I'm going to create the simulation diagram, okay, in a slightly different way, though. Okay. Where's my handwriting? Where did it go? That's weird. All right. As a matter of fact, if you remember in the previous lecture, so in previous lecture, okay, we have a case, we call that nested programming approach. So I'm going to rewrite that the formula here. Y of z over u of z equal to, how much is that? 0.5 z squared. Plus that. Over 1 plus 0.6. Right, I need to write it into the DSP format. cut into DSP point. Okay, so right from here, I'm going to rewrite this equation like this right here, okay? Like this. See if you can catch this. So basically multiply the u to the numerator and multiply the y with the denominator. Okay, so multiply u with the numerator and the y with the denominator. And then move all the y's, multiply this whole chunk to the right side and combine with the u of z over there, but with some groupings at here. Okay, so this is going to be what it looks like here. Okay, z to the power -1 0.5 u of z, okay, minus 0.6 y of z plus z to the power -1, okay, and u of z minus 0.5 y of z. This 0.5 here. And then plus another z to the power -1. Okay. And the last term here is just minus, so basically 0 times u of z and minus 0.3 y of z, and then bracket, so several brackets here to conclude it. Here, this is nested here. Can you see that, right? It's a nested thing here. Really, actually, it's nothing different. It's basically, you see here, it's the same way as we did in the first lecture. If you look at the first one here, this is 0.5 times z to the power -1 times u of z here, right? Yeah. And then you have this 0.6 z to the power -1 times y of z. So when you multiply this z to the power -1 into here, you know, that's this term, subtract this term, multiplied by y of z. Okay? Yeah. And then the other one here, because this is net to the power -2, you take out another -1 here. So this one times into here, this one times into here, this becomes z to the power -2. Right? So it's essentially just the different ways of manipulating the original, you know, transfer function, pulse transfer function. Okay, yeah, nothing different. Yeah. Extra square, where? Here?
The bracket at the end of that line should be.
The bracket at the end of the line. You mean this bracket here? It shouldn't be here? Oh, it should. Yeah, you're exactly right. Yeah. Excellent. Yes. Good. Good catch. Yeah. Right? That's basically nested here, right? You know, there's the x between an egg, and a net x inside another egg. Okay? Yeah. So the simulation diagram that we're going to build at here, it's purely based on this this expression. Okay, this expression. So let's see, how do we build this simulation diagram now? Okay, so here's what I do to build this simulation diagram. Okay, on the top line at here, this is my u of k. Okay, or u of z. Okay, yeah. Now we have, here's 1, and here is 0.5. Okay, so 0.5 times u of z, and 1 times u of z here. And how does that subtracting goes here, right? So you see this one here, the first one here, the most inner side of the net program, this block at here, and there's no u of z, and just the feedback of 0.3 y of z. So let's say my y of z is over here, okay? My y of z over here. So what are we feeding back? We're feeding back this y of z times, by how much? Times negative 0.3, right? Times negative 0.3. Okay? Yeah. And then we're feeding this back. Okay? And this guy will time a negative z to the power negative 1 block. So we'll put a z to the power negative 1 block at here. Okay? Yeah. And then whatever coming out of here, right? Whatever coming out of here is going to be used over here, right? Going to be over here. So this block is the signal at here, right? This block is the signal at here, and that signal will be added into this u of z times 1, right? This is 1 here. So basically, coming out of this block will be added into here. Okay, will be added here. And at the same time, it's going to subtract, right? It's going to subtract 0.5 y of z here, which means, right? Basically, feedback y here multiplied by negative 0.5, add these together. So 1, 2, 3. So 1, 2, 3. So all three together give you which one? Give you this block here. Yeah? Okay. And after this guy here, it gives another delay. So this delay here is this delay. Okay. It's this delay here. So that delay adding to these two pieces. Okay, adding to these two pieces by feeding back this one here, negative 0.6. Okay, yeah. The last one, another delay at here. Okay, there. So that completes this simulation diagram based on that expression, the nested programming. This is the nested programming. Okay, the nested programming.
Why did you use that delay zone?
Pardon me? What do you use the delay?
The very top bar that you got like the 1.5. Why doesn't the delays along there? So your U should be multiplied by.
Sorry, didn't quite get your question. Why do you have this one here, you mean?
Well, you don't like if you like 0.5 u z, for example, right at the beginning of your yz equation. Why is that multiplied by z to the negative 1?
Why? Which one multiplies z
Your
to?
equation that you have written.
Yeah.
You got z in front, z to the next power of negative 1 in front.
Yeah, this one here.
Yeah, why isn't like uz right to the right of it multiplied by the?
You mean why didn't I use this to here?
No, like why is the 0.5 uz, why isn't it not multiplied by a delay?
Or why this one didn't multiply by the delay?
Yeah, that delay should be fed into the 0.6 y.
Oh, it did, right? Because when you put this signal up to this stage here, it'll multiply this delay here, right? Yeah. Okay, it just didn't do it here, right? Yeah. Okay. Did you see that, right? You know, I've been away from digital signal processing, design digital filter. When you design digital filter, there are two different ways. There's the IR, there's the FIR. You know, basically when you design a filter, actually this is one way of building up the block, isn't it? Recall that? No? Yeah. No. Anyway, so, but in short, right? This is the nested programming, and this is the diagram based on nested programming. And then the next stage, and just like the control canonical form, we choose the state variables, right? So how do we choose a state variable? So as I said, you choose the state variable. A rule of thumb is a signal right after the z to the power -1 block. Okay, so which means which 3 locations that we're going to choose our state space variable? Here, here, and here. Okay. So you can choose. Let's say I call this is x1 of k, and x2 of k, and x3 of k. Let's see. Okay. Yeah. Is that okay? Yeah. So now I can build my state space model now. Okay. Before we build a state model, if I use the coefficients, and this is my b1, this is my b2, this is negative a1, negative a2, and negative a3, right? Negative a3. So if you build our model here, so let's say what do we have here? We're going to end up with this. Okay, we're going to end up with x of k plus 1. So you can basically try this. So if this is x3, then what will be here? This signal here is what? x3 of k plus 1, right? x3 of k plus 1. Okay? Yeah. And same thing, this will be x2 of k plus 1. This will be x1 of k plus 1. Okay, so, but if you go through the same procedure as we did, you'll get this one here. 0, 0, negative 3, and 1, 0, negative 0.5, 0, 1, negative 0.6, x of k, plus, okay, 0, 1, 0.5, u of k. Okay? And y of k, this y of k is easy. Y of k is actually the same as x3 of k. So y of k is 0, 0, 1, x1 of k, x2 of k, x3 of k. Okay? Yeah. And that's the state space model, okay, for this so-called observable canonical form. Okay. Is that good? Yeah. Okay. Now take a look at this observable canonical form and that control canonical form that we have just derived. What is the difference between this matrix and that matrix there? Exactly. Yeah. Right. So basically the connection now between that control canonical and this one here is just a transpose, right? Transpose here. So in other words, if you have already obtained a control canonical form and you're required to obtain the observable canonical form, so what do? You can actually just simply do a transpose. Okay, transpose. Okay, so this is a little bit summarized regarding this difference here. So if A, B, C, D, okay, A, B, C, D, okay, is for control canonical, okay, then the corresponding is A prime, C prime, and B prime, and D, okay, is for the observable. Yeah, notice this is not B prime, this is C prime here, okay, this C prime. C prime corresponding to this B at here. Does that make sense? You see here, the original B at here is, which is the B? This is a B, 001 here, see, right? 001. What is the C at here? 001. The transpose of this is that B there, right? There's that B. Okay, yeah. And the original C is 0.5, and now this is the B here, right? See, right? Yeah. That's how you basically construct the things in here. Okay? For more generic, okay, format, look at the handout that they gave it to you. Okay, look at the handout. Now, in the handout, again, I actually presented two different observable canonical form, I believe. Yeah. Okay. So in the handout, there are two different observable canonical form. Essentially, the difference is if you define this is x3 of k, x2 of k, and x1 of k. Okay, if you define the state variable basically differently, you get a slight different matrix. Okay, appears. Okay, but you are still talking about the same system. Okay, right? Yeah, so bottom line is, my purpose is for you is to basically understand how would you get from the observable or control canonical, okay, giving a pulse trans function. But in the future, okay, when you do design, when you're trying to obtain a state space model, and you don't need to go through the steps, building the simulation diagram every time. So what you need to do is basically just pick up the formula over here, pick up one of them, and just use the coefficient properly, right? And that's my requirement. Is that good? Yeah. That's a simplified requirement, though. Huh? Okay, so now you basically you see the connection now as to the control, the two most commonly used one, control canonical and observable canonical. In MATLAB, okay, sometimes when you use a MATLAB, you got to be very careful, though, huh? Yeah. So let's say in MATLAB you have a numerator defined, and you have a denominator defined, and you have a sampling time defined. That's basically what I give you in the handouts there. And then you define a system, a continuous system, okay, using TF function. You define a discrete system. Okay. You define a discrete system using this TF function. Okay. Yeah. And then in MATLAB, there's a command called transfer function to state space. Okay, transfer function to state space. So that function takes the numerator and denominator and return this A, B, C, D. Okay, return this A, B, C, D. Okay, so the default, if you check the default, the A actually is a control canonical, okay, from this function here. Okay, the default. Okay, yeah. But the B matrix and C, often in time you might find actually you get the different results. If you do it manually, you probably get a different results from the MATLAB. Okay, doesn't necessarily you're wrong or doesn't necessarily he's wrong. And it actually all it boils down to the statement I just said there. What's the statement? There are infinite number of ways deriving state space model. Okay, yeah. And when we come to the project, I actually require you to do some hand derivations, okay, so that you know which state is which. So basically what I mean is, here you have x1 of k, x2 of k, x3 of k, right? If you purely using MATLAB tools, so the x1, x2, x3 of k that you're getting out of the tool, you don't necessarily know what they represent. But if you do it manually, You said, okay, I'm going to let x1 of k represent the position. I'm going to let x2 of k represent the velocity, something like that, right? So you know exactly what they are, right? Yeah.
What happens if you have like a nonlinear MIMO system?
I don't know. That's a big jump.
Like most systems don't fall into that linear CISO category.
Sure. Well, it's always a compromise between the amount of calculation and the amount of what should I put it, knowledge that you want to directly have. If you're not in your system, then if you purely rely on the math model here, right, mathematic tools, so you probably had to do that, right? Otherwise, if you do it all manually, if you linearize it, then you look at it. Okay, I'm going to pick this as a state, pick that as the second state variables. You may not, it may not be feasible, right? So, but bottom line is, here's a mathematical model. It all boils down to how much you want to have knowledge you have into each one of the state variables, right? Yeah. So when there's one assignment question in the last year. So when a student did a simulation and he got a totally different results from mine, because he used MATLAB. It's all using MATLAB. Okay. The reason is basically what I said just there. When you use all your MATLAB, then the state variable is actually different from if I do it manually. So, but doesn't necessarily mean the output of the system will be different though, huh? Right. Okay.
So that mean for like the graduate project, you suggest we pick like a CISO system that's linear?
Yeah, you can. Yeah. If you have a multiple input, multiple output system, nonlinear ones, you may have to linearize it first, right? Yeah. Okay. So, still got a little bit of time, so I'm going to show you another type of basically state space model. Okay. Just to give you a taste, how can we get? Okay, let's say this time I'm going to give you a diagonal. Okay, so it's over here, diagonal. Okay, so here is the example. I'm going to use it here. Okay, y of z over u of z equal 1 over over 1 over this guy. And you can easily decompose this. You'll see that this is, it's this. So it has two roots. Okay? You got two roots set here. Okay. So if I'm gonna use the partial fraction on this guy here, I'm gonna get this. Okay, apply partial fraction expansion, so I'm gonna get this guy here. Okay, and I can go one step further at here, so basically write it into the DSP format. Okay, yeah. So it's right in the DSP format. And now we build our diagram. Okay, so now we build our diagram based on the expression right here. So how does the simulation diagram look like? Now basically it's addition, right, of two blocks. This is one block and this is one block. Okay, one block here. So if you remember in the continuous system here, this is G, this is H, and the transfer function for this kind of block is what? It's g over 1 plus gh, right? 1 plus gh. Okay. So for this particular one here, for each one, this block here, actually I can consider this z to the power -1 as g, right? As g. And I can consider this 0.9 negative 0.9. I can consider this exactly negative 0.9 as the h. Okay, so h is negative 0.9 and g is this block. Okay, this block. So then I'll build two basically closed loop. One is for this, one is for that, and then parallel, add them together. That's what happens, right? Yeah. So one block is for that. Okay, negative feedback. So negative feedback. Okay. And the other block is negative 0.8. Okay, so the other block is this. Okay, negative feedback. So the two blocks. The output of the first block, right? Output of the first block times 10. Okay, output of the first block times 10. And output of the second block times negative 10. Okay, yeah. And the output, right? The output is addition of these two at here. So you have the input u of z. So basically the u of z is given to both of these two blocks here, or u of k, okay, right? And output here is the addition of these two. You get y of z, okay, or y of k. All right. So here's the simulation diagram based on this expression right here, right? And then the second step is, remember what do? You basically gonna pick up the state variables, right? The state variables. State variables picked up right after this z to the power -1 delay block. So let's say I'm gonna pick this is x2 of k, and this is x1 of k. Okay, yeah. So based on this choice of your state variables, and apparently this is x2 of k plus 1, and this is x1 of k plus 1, you will be able to derive your state equation x1 of k plus 1, x2 of k plus 1, okay, equal to 0.9 at here, 0 here, 0 here, 0.8 at here, x1, x2 of k, okay, plus 1, 1 u of k, okay, and y of k equal to 10, negative 10 times x1 of k, x2 of k. Okay, you'll be able to get this. Okay, so simply just look at this if that makes sense, right? See that y of k equal to 10 times this, negative 10 times that. Okay. Oh, actually, there's a. This should be what? Should be negative here, right? So negative 10 times x1 of k, and 10 times x2 of k, right? Yeah. That makes sense? So this is basically what we call diagonal format. And the system matrix is in the diagonal format. And what are the diagonal elements right here? The value. What are the value of diagonal elements? They are the poles of the system, right? Yeah. As a matter of fact, okay, and as long as the system is not singular, you can diagonalize the system okay, so that the diagonal elements, okay, of the system matrix that here A is all the poles of the system. Okay, yeah. And one of the lecture we're going to the similarity transformation. Okay, so we'll look at that nature, right? Yeah. How do we transform the system matrix to whatever format that we want? Okay, one particular format is this diagonal. Okay. You mean this should be 0.9? Oh, is that right? X 2. Oh yeah, you're right. Okay, so maybe I should do this. Okay, maybe I should do this. I'll just change this to so I'll just change this to x1 here and x2 here. So now you can't hold me accountable for that anymore. Yeah. So I guess now I have to change this back to negative. Good. Yeah. Okay. Yeah. So you know, look at the lecture notes. There are a couple other ways of deriving the state space model. Okay, or different ways of building the simulation diagram. Okay. Yeah. But in essence, you know, you should get a sense is there are infinite number of ways of representing, using state model representing the original system. Okay. Yeah. Any questions? No good? All right. Yeah. Okay. Okay.